Okay, we are now recording, and we'll start with the syllabus. Now, I'll try to do this, like I said, as quickly as possible. This is Math 125, Calculus 1. We meet Monday, Wednesday, 8 to 10:40 in this room, so you know all that. Here's my name, Charles Fowler. My office on this campus is room A265. Now, here's how you get there from here. You go out the door here. Here we are in this corner classroom right here. You go out the door, take a left, go down this half flight of stairs here, go almost all the way to the end of the hall. Before you run into the wall at the end, there's a stairwell, but just before the stairwell is my office, 265. It's in between the mechanical room that looks just like this and the stairwell. So it's hard to miss. If any of you have been here for orientation, right across from the orientation classroom. Okay, that's where I live on this campus. Okay, I'll get my office hours in just a few minutes. That's where I am here. Now, on Fridays, I'm usually on the Birmingham campus, Birmingham West campus. However, in the summer, we typically, did I get you when you came in? No, okay. Let me get your name, please. Second, Jordan. Okay. I remember seeing it, Jordan. I'm going to see if I can find you. Oh, yeah, Jordan Wells. Is that what you got by Jordan? Okay. All right. Were you here last time? You weren't. Okay, so this is your first time. Anyone else who's first time? Okay, sorry, what's your name?
Catherine.
Okay. Catherine Petty, is that what you said? Okay. And you go by Catherine? Okay. All right, good deal. By the way, folks, the second page is coming in really strong. Only one person out there. The first page, woo, 5, 6. Missing from that. So, first page people, get your both folks here. Okay. All right. Fridays on Birmingham campus. I don't know if you're familiar with Birmingham campus, but it's the Birmingham West campus, sort of the main campus. There's a big quad in the middle of the circular drive that circles it. There's the administration building here. That's the A building. The B building's a long classroom building. It's called the academic building here. That's the building I'm in. And then there's a C building here. That's the science building. And the D building is the library building. Okay, it makes it sort of a quad. I'm in that B building, far in. There's 2 floors, the basement floor and then the main floor. I'm on the main floor. When you come in either end, you go up a half flight of stairs, and then I'm the first door on the that you get to at the top of the stairs on that end, the end toward the gym, the tennis courts, and the baseball field. However, most of our buildings are old buildings with not great insulation. As you see, someone put a piece of paper there to keep the windows from rattling when there's strong wind outside. It's not a very tight building, so in the summertime, it gets pretty hot. Old air conditioning system. Take a lot of energy, so they decided let's close the school down on Friday and Saturday. Fall and spring we have Saturday classes, Friday evening classes. They said let's do away with it. So we go in June and July to a 4-day work week, 4 10-hour days, everybody here on campus, and no one's here on Friday. But this Friday, even though it's in June, we will be here, okay? I'll be on the Birmingham campus. So June and July, the rest of the Fridays in June and July, nobody's here. The campus is closed. Then in August, we have one Friday after we come back in August. When we're here in August, I'll be back on the Birmingham campus. B122, the academic building is the B building. And this is my number on my office here. Here's the number in the office that I go to here. Now let me tell you something about my phone numbers. The voicemail is inconsistent. Sometimes you can't even leave a message. Sometimes you leave it and I can't hear it. Sometimes it might come through okay, but you never know which it's going to be. So I would say only call this number during my office hours. I'll get to my office hours in just a minute. Okay? Don't try leaving a message because I don't know if I'll get it ever or in time to respond. Do not leave a message on this one because, like I said, I'm only here on Fridays. This office belongs to, or the phone belongs to, or is addressed to a grant coordinator who's part-time and she's only here Monday through Thursday. So when I'm over there, I use her office on Friday. So if you leave a voicemail here, she'll hear it, but she won't know what you're talking about because I can't access that voicemail. So basically, don't leave voicemails with either one. Call during my office hours here or office hours here. If you don't get me, hang up, try back again in a few minutes, maybe down at the restroom or something like that. Here's my email address, cfile@bostonstate.edu. And right now, I'm way behind on email, so if you've sent me something recently, I'm still trying to catch up because I've been trying to get my syllabi and everything else done, and all the first of the term stuff. So I'm a little behind, but I'll try to catch up as time goes on. Now here's my office hours, okay? I usually am on campus, usually before 7:45, but that's what time I shoot to get here. Now if we have bad traffic or bad weather, today I got here on plenty of time, but 7:45 to 8, only 15 minutes in the morning. And then we have this class at 8, it goes to 10:40, then I have a big 20-minute break before my Calculus 2 class. It starts at 11 and goes to 1:40, okay? But I was scheduled for 2 physics classes. It turned out that we had to stack those classes and Dr. Bryant is teaching those. So that freed me up in the afternoon on Mondays and Wednesdays from 1:45 until 6 o'clock. Big chunk of office hours. I've never had that luxury in years, okay, to have that many office hours in one big group. The reason is I pay for it on Tuesday and Thursday. Because on Tuesday and Thursday, again, I'm here at 7:45. I have an 8 o'clock class. It's a 3-hour course. So it's 8 to 9:50. I have a big 10-minute break before my that's differential equation class. And then at 10, I start linear algebra. And then that's 10 to 11:50. Have another big 10-minute break and start my physical science class, which has a lab with it. So it goes from 12 to 1:50 with the lab from 2 to 3:30. And then I have a 30-minute, it looks like on the schedule, break, but it's not in the office. I'm driving to the Birmingham campus because my evening class that goes from 4 to 5:30 is on the Birmingham East campus. So you can't really catch me in between those 2 classes because I have to book it to the Birmingham campus as quickly as I can. But once that class gets over with at 5:30, I stay there until at least 6 o'clock. Last night I was there longer. Most nights I'll probably be a little longer. But that's the other. 15 minutes at the beginning of the day, 30 minutes at the end of the day. This is here on Bessemer. That's on Birmingham East Campus. Okay, Wednesdays just like Mondays and Thursdays just like Tuesdays. Fridays, this Friday and last Friday too, but that's no good to you. This Friday and the first Friday in August, I'll be on the Birmingham West Campus from at this location, from 7:45 to 11:45. Now, I put that down that way. I'm usually there well past 11:45, and quite often there before 7:45. Okay, let's look at the course description. Now, this is not something I made up or did or anything else or anyone here at the college. This was done by conjunction with the 4-year public schools in Alabama, the 4-year and universities and colleges, public, and the 2-year system. They agree, if we do this, they'll give you credit for it. So, what we're going to do, I'm going to try to hit it fast. We're going to deal with limits, derivatives, and derivatives of algebraic, trigonometric, exponential, and logarithmic functions, definite integral, basic applications, area problems, and then application of the derivative are covered in detail, including approximations of error, differentials, maximum minimum problems, curve sketching, blah, blah, blah. A lot to cover. A whole lot to cover. Okay, Daniel's here. You were here last time too, right? Okay. Anyone else come in since when I wasn't looking? Okay. All right. So anyway, you'll see these concepts show up again. A lot to cover. Okay, prerequisite, basically finish Math 113 or 115, whichever your school had, or scored for it. So hopefully you're in the right place. The textbook is this one. Calculus, written by Ron Larson and Bruce Edwards. It's 11th edition, okay, and it's a Cengage learning text. Recent, as in this year, copyright dates, it should be good for a couple or 3 years. Graphing calculators, you don't need it, but if you have one already, or you might find it useful, I don't require that. Paper, graph paper, pencils. Now, whoever wrote this put pencils. I don't care if you use ink, but I'll make a confession to you now. When I do calculus, I tend to make errors, okay? So I like to use pencil for myself, so it doesn't have blobs all over the page. And you'll see that, won't you? Okay, never mind, don't answer that question. Okay, so that's what we have here. Okay, this thing on Blackboard, I'll let you read it. I find it pretty obnoxious, some of the statements in it, but I won't go into that now. Is everybody familiar with Blackboard? Any of you not? Okay. It's a relatively easy package. And by the way, since we're talking about Blackboard, let's talk about it. When you get into it in this class, you've probably already been there. The home page here, okay? That home page, there's a series of blue tabs, or at least in the instructor side of things, they're blue. I don't know what yours are. Now, this is sort of new. They just came out with this new format sometime in the spring, okay? So if you were here sometime before that, you may not have seen this new one, okay? It has a whole bunch of blue tabs. Before, it was only about that many blue tabs, and they were really straightforward. Content, that's where I put everything, okay? Now they have other stuff, so they have My Syllabus, okay? At about the third or fourth blue tab there. When you click on that, you'll see the syllabus, okay? Updated, you know, I changed some things on it just yesterday, okay? So that's where the syllabus will be. Then somewhere down here on my computer, you can still see it. It's almost at the bottom, but you may not see it. You may have to scroll down a little bit. Like I said, this is a long list of tabs. There's something that says class handouts and more. Okay, content made a lot of sense. That doesn't make a lot of sense because they're not really handouts. Okay, but anyway, if you click on that, you'll see the rest of the stuff. Now, what's the rest of the stuff? The research paper instructions are there. My locator card is there. We'll look at both of those before we finish today. Okay. I put all of the chapters we might do, okay, all the sections, the PowerPoint, they're there. I put, let me get your name, please.
Tiara Sonato.
Okay.
Let me spell it.
Tiara? Is that?
Yes.
Yeah, is that how you pronounce it? Is that what you go by?
Yes, sir.
Okay.
Tiara.
Tiara. And were you here last time?
Yes.
I thought so. Okay. Okay. Anyone else come in since the call roll? Okay. Going over the syllabus because I know Mr. Rossi didn't quit last time. Okay, so I was talking about Blackboard. There's the syllabus is in My Syllabus tab. This is on the home page of Blackboard. And somewhere down here you'll see class handouts and more. Really descriptive, okay? And there you'll find the research paper instructions, my locator card. You'll find PowerPoints for every section we could possibly do, probably more than we'll do. They're there. And also, over the years, I found some websites. I've had students tell me about websites they found useful for the course. So I put those there. There's one called Slater, one called something with calculus, and I don't remember. There's several. I can't remember all the names now. But some of them are linked to the book, and some of them are not. Those that are linked to the book are linked to the previous edition. Obviously, they haven't updated, and this is a fairly new edition. But there's very little that has changed. So those are there. And then probably the last thing that you'll find there, I think it's at the very bottom, is a link, a web link that says Math 125 YouTube videos. That's where this lecture will go in every class that I record. As soon as the class is over, I send it to YouTube. It usually takes a couple of hours to get loaded to YouTube, and then sometime in the afternoon, those office hours I have, once it's loaded, I will move it to the playlist. So if you click on that thing in Blackboard, you'll go straight to the playlist. Now let me tell you what's in the playlist. You'll see it's full. It doesn't just have one thing. I have left in there all the classes that I had last time I taught this, which was in the spring. So you can look ahead and see what's coming if you want to. But the syllabus will be, if you see one at the top, that's last spring's. At the bottom, and they always put the things I load at the bottom. So these will be coming in, and as I cover things I've already done before, I'll delete them at the top. But I'll leave the whole thing out there so you can look ahead. Say you're going to have to miss, you know you're going to have to miss, you can look ahead and get a good idea what's coming up. Okay? So, there's Blackboard. Okay. Now, also things about grades, I'll put grades in, especially when I have office hours in the afternoon. I'll try to get all the grading done that afternoon and put your grades out there. I won't promise I'll always have it done that way, but I will do my best to get that done. Because they do pile a lot of administrative stuff on us in the summertime, and I'm a department chair, so I get way more than I want. Okay. So here are the student learning outcomes. And if you'll notice, this goes right with the course description. Students will find limits graphically, numerically, and analytically. That's basically chapter 1. Students will take the derivative of functions using product and quotient rules, higher derivatives, chain rule, implicit differentiation. That's chapter 2. Students will apply the derivative to extrema. You probably saw that in the course description. Curve sketching, optimization, Newton's method. That's chapter 3. Okay? Students will approximate and compute area using the definite integral, and we'll use the fundamental theorem of calculus. That's chapter 4. I'll go and point these out to you here. Okay? Students will use the, let's see, where am I? Okay. Students will use computer and graphing calculator to illustrate knowledge of concepts such as limit, continuity, and extreme values of functions. That's done in all the chapters. Someone else wrote these competencies or student learning outcomes. And students will research and write on the topic in calculus, and that's your research paper we'll talk about in a minute. Now, I did want to point this out to you. You don't see it written here, but there's also a chapter 5 here that's logarithmic and exponential functions. And I don't know why, let me back up a minute here. I meant to say this when I was talking about it in a rush. We've recently, like last spring was the first time I've used this book, so I've taught it once. I like the author. I don't like the publisher, okay? But this author is one of the best authors I have had. Now, the calculus part, he does as well as anybody. In fact, much better than the last. But here's what I like about it. On the cover here, you'll see with Calc Chat and Calc View. Now, what is that? Okay? Every problem set at the end of end of each section has some problems on it. Now, they're even in odds, and they're grouped according to material. I'll give you, your assignment will always be the odd numbers from this group, the odd numbers from that group, the odd numbers from that group. Why the odd numbers? 2 reasons. Number 1, the odd numbers have the answers in the back. So when you're doing the homework exercises, if you get an answer, look in the back, see if it's right. If it is, go on. If it's not, see if you can figure out what you missed. If you have trouble finding out what you missed, you can then go to calcchat.com. It's a free website, okay? And you'll find it. This author has done it, and he'll work out every one of the odd number exercises. Every one of them. Okay. Now, you'll see in the homework exercises, some of them will have, I think, a red letter. You know, when they're number 1, 2, 3, 4, 5, number 13 may be red. Number 17 may be red. And if that's the case, those are worked out in great detail in calcview.com. Okay? Not one from every section, one from every topic covered, but most of the topics will have something from CalcView. And he does a more thorough job on those, explaining everything. The others are just worked out. So it's a great tool. I've not found any author who does that. There's something else he does, and I'll wait till I get there. I'll point that out. There's another website called larsoncalculus.com. And in that one, he goes in more things. There are examples in the book, and following each example, he gives you a quick check or something like that right after it's the very same type thing. And there on larsoncalculus.com, he has those worked out. So it's just incredible. He has 3 websites that are free to use. Now, by the way, do any of you really love WebAssign and want to use WebAssign? I think there is one student who's not here today who does want that, because her mother wants that, okay? Because her mother uses that when she teaches. So I'll probably get WebAssign set up. I just don't know when. I'm going to try to get it started this afternoon, but it takes me a while. It's not an easy thing for me to work on. I don't know how it is for y'all. Are any of you familiar with it? Did you like it?
It was all right.
It was all right. Okay, well, I'll get it set up so you can use it if you want to. I'll never, you're shaking your head, no, I'll never make an assignment on it, but it'll be there for you to use whatever's there. You paid for it, basically, when you purchased your book. Yeah.
So all of our assignments are going to be paper-based.
What's that?
All of our assignments are going to be paper-based. We have to turn it in physically, right?
Yeah, it'll be just out of the book, yeah. So therefore, if someone bought a used book, couldn't afford a new book or whatever, you don't get penalized. If you got a new book, you have access to this other stuff, okay? And it's nothing that you'll be graded on, so you're all graded the same way. Does that make sense? Okay. All right. So, chapter 5 now. The last time I taught it in the spring, we had weather days, we had holidays, Monday, Wednesday class, and we didn't get to logarithmic and exponential functions. I hated that. This time we're going to try to, but already we got holidays and I've already missed a day. So, let's talk quickly about how I'm going to evaluate you and assess you. And basically, as you saw here, I didn't point this out. Let me go back and point it out. After each chapter, you have a test. Okay? Now, I have a question for you. Do you prefer in-class test or take-home test? Really? My goodness, what a shock. Okay. We'll probably do take-home test. Okay? Number one, sometimes calculus problems take a long time to do. And if you get stuck on one, you can just rack a whole test, you know, if you don't plan it well, if you're limited with time. So I want you to have the time you take. You can have your book. You can have resources. Guess what? If you were working for me in a company doing this kind of stuff, I'm not going to ask you to, oh, you can't have any resources available. I want you to solve these problems, but you can't look at anything. No, if I hire you, I want you to use every resource you can get and figure out how to solve whatever the problem is, the issue. That's the same thing I want to hear. I think that's part of the learning process, to use your resources and to do it. Now, does that open it up for abuse? Probably. But guess what? If you're in pre-engineering, which I'm guessing most of you are, right? When you're out in the field, it's not going to do you any good to cheat in this because you're not going to be able to do the job. You can't, okay? So, okay. Y'all are good people, so I'm not worried about that. So we have a test at each one. We'll have the research paper. We'll have the final exam. So the following is a breakdown of how we'll evaluate. Research paper is required. It will count as a test grade that cannot be dropped. Cannot be dropped. Everybody does research paper, okay? Now, we'll talk about that. It's not a big deal, okay? Chapter test given after each chapter. The lowest chapter test score may be dropped, okay? The reason I put may in there, don't turn in a research paper. You get a 0 on that, you're going to need every test score you can to bring that up, okay? So don't go there, but that's why I don't say will be dropped, it's maybe. The final exam, by the way, I'm going to go back and change this. I meant to earlier. I didn't realize I had changed this. The final exam will be your last exam. Whatever your last exam is, that's your final. It's not going to be comprehensive, okay? But guess what? Math, especially calculus, builds on itself. So that last chapter test is going to be pulling from everything else you did before. So in a sense, it's kind of comprehensive. But I found out last time I didn't have time for a separate comprehensive final exam. We're just going to have the last chapter test will be your final. That will not be able to drop. All of the others you can. So the lowest chapter test score, except for the last one, may be dropped. The final exam, which will be just your last exam, will not be dropped. Okay? And that will count as one test score because it's going to be take home just like the others. So there's nothing special about it. except it can't be dropped. And I'll grade everything on a 100-point scale. The average will give you, hopefully, just like you're used to seeing. And by the way, when they came out with this new syllabus, they just throw in plagiarism everywhere you can find it, okay? So blah, 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 okay. When I get your averages, 90s are A's, 80s are B's, 70s are C's, don't go down here, okay? If it looks like you're heading this way, come on and withdraw from the class, okay? A D or an F is not going to help you at all. Now, some of you are Lawson students. Most of you are transient students, right? Okay, I see about 4 Lawson students. Most of you are transient, okay? Your schools are not going to accept a D, are they? Okay, so now, Lawson students, we're not going to accept a D either. So nobody's going to get any credit for a D. All it does is pull down your grade point average, okay? F really pulls them down, okay? A W does not hurt your grade point average at all. Does not affect it. Sure, if you're on federal financial aid or some other thing and you have to retake a class, you can only retake it once. But that's whether you made a D, an F, or withdrew. So there's no difference there. The only difference is a W doesn't hurt your grade point, these two. So I say do that. Now, I must admit, I changed the sentence here. Whoever wrote this obviously was not a math person. It said, the instructor rounds the grades, and here what she said was, I think it was a she, always to the student's favor. Always up, never down. I mean, put that in there, in parentheses, focus on that. And then here was her example. For example, a 79.5 will be rounded up to an 80%, a B, but a 79.4 would remain a C. Well, guess what? That's rounding down. Okay? So she said, always rounds up, never always to the student's advantage, but then she gave this as an example. So I just changed it and said, round the grade normally. This is how you round grades. A 5 or greater is going to move it up. A 4 or less is going to leave it alone. Okay. So, sorry about that, but it was just wacko the way she had it. Okay, here's talking about absences. Try to, I'll let you read this. Withdrawals, I just talked about that. Makeup work. It's kind of hard to imagine. You got take-home tests. What does makeup work with a take-home test? Well, what it means here is this. Try to get your test done within a week. Now, I'm not going to hold your feet to the fire on that, but try to get it done within a week because there's going to be another test coming up real soon. The main thing I don't want is for you to have one test that you haven't turned in when I'm passing out the next test. Because here's a couple reasons for that. Number one, you're getting farther behind. But even more important than that, since I'm grading these, as soon as I get them, I'm going to grade them. Once they're graded, you can look at them. But I can't return it to you until I get them all in. So if you are 1 or 2 tests behind, that means I can't return the papers to all the rest of the class. Because if I return papers, eyes may fall on the correct answers and then dilute your score, giving the recalcitrant student a better score. That's not good. That's not fair. It's not. So I won't return papers until I get them all in. So please get them in before the next test. Because I don't want you making the same mistake on the second test that you made on the first test, and you don't know it because you didn't come and check to see what you missed. Okay? So please get it in as soon as you can. Aim for a week. 2 reasons I give you a week. Number one, we always have a class period in between so you can ask questions. You don't understand what I'm asking, what the question means, you can always ask questions. Now, by the way, here's one question I will not answer. Well, I will answer it, but I won't do it. Can you do number 7 on the test? I'll answer it. Yes, I can. Okay? But I'm not going to do number 7 because that's what I'm testing you on. But what I will do, any problem you find in the book, can I do this one? Sure. Let's do it. So therefore, find something similar in the book and I'll be glad to work that. I won't work the test question. So that's why I give you a week. The other reason, you always have a weekend. In case you work during the week, you just don't have that many hours, you always have a weekend that you can work on. So, try to get it in a week. If you need more time, take it, but just get it in before I'm ready for the next test. Okay, lateness, I'm going to try to always start on time. Usually I'm here early, only if there's going to be traffic or something like that. Okay? it would be a problem. Now, as I said, they are all over this academic integrity, and they just have pages in the syllabus about this. I'm going to let you read it. Please don't plagiarize, okay? I think they even have on Blackboard a package, a tab there you can check to see if plagiarism happens. That may only be for instructors, I don't know. But see, use any tool you can. Cheating, okay? Now, like I said, take-home tests do open it up for abuse, but it's not going to do you any good. Okay, you might get a better grade, but if you don't know this material when you get into your engineering courses, it's going to bite you really badly then. And you don't want to go there, okay? So I'll leave that alone. Professional decorum. Oh, that sounds so impressive, doesn't it? Okay. Sorry about that. Okay. Yeah, read this, go over it. Let me put it this way. If you're doing something that's distracting to other students, don't do it. Go out in the hall. Do it somewhere else. If you have to text somebody, you may have kids, you may have parents, you may have people you're taking care of. If you need to, if you get an emergency message, don't start talking on the phone here. Go out in the hall, okay? I don't mind, okay? Don't snore, okay? If you are that tired and need to sleep, if you're bothering somebody else, go somewhere else and do it, okay? Blah, blah, blah. This is a long class. 2 hours and 40 minutes. If you need to go, go. Okay? Sometimes I need to go. I'll go, okay? So, unnecessary traffic. Don't just be all over the place. If you wake up late, miss breakfast, and you can't function without breakfast, I'd rather you be here even if you're eating breakfast. Now, if you're bothering other people, if it smells that good, then you go to a back room or something and finish breakfast, but whatever. But, and if you need the caffeine because I'm Mr. Sandman and I'm putting you to sleep, then it's okay. I'm not. Inappropriate clothing. Again, if it's distracting and bothering other students, please don't do it. Have enough respect for your fellow classmates. Okay? But y'all all seem to be adequately dressed, so keep it up. Okay? Sunglasses, if that helps you think I'm not going to see you sleeping, I don't care. I'll let you decide that. I'm not as picky as probably I should be. But you know what? I only have a few more years. If they want to take away my birthday, they can. Okay, I'm not as, well, never mind. Okay, course concerns. If you feel like I'm not giving you a fair shake, here's what you do, okay? Read this, go through it. I'll help you with it. I'll even help you write me up. I do care. But, I want you to have a full chance to do whatever. So, I'll let you read that. Now, this next one, I don't want to underdo that. Whoops. Okay, I may have been making fun of some of the others, but I don't want to make fun of this one. Discrimination, harassment. I've been here I think this is my 21st year or something like that. Originally we were at Bethlehem State Technical College, now we're at Wilson. In this building, almost in this classroom the whole time, and I have seen basically almost zilch that would fall under here. That doesn't mean it hasn't happened, but it just hasn't happened in front of me. And that's the deal. Who's going to do this when I'm standing around? Probably no one. But this is what I want to ask you to do. If you see or even sense that anything like this is happening, please let us know. We don't want it to happen anywhere, and especially not on our campus. So please let us know. I am really dead serious about this one, okay? And you can read all the things that it covers. We like to nip it in the bud and not have it happening here. And so far, like I said, I haven't seen it, but I don't want it to happen. Okay? Okay. Americans with disability, I've already told you, I'm hard of hearing. So I'm sort of sensitive to this issue. If you have any kind of thing, whether it's physical like hearing or vision or, something more like dyslexia when you read or whatever it may be, all those letters they put out to, A, D, D, or whatever those things are, any of that kind of stuff, bring your documentation to the college. I don't need it. I'm not a professional on this. Dr. Renee Herndon is here on this campus, Office of Disability Services. Here's her phone number. She's on this campus. I can show you where her room is. If you know where the admissions desk is, if you came to the right, you go to the left, and down that short hallway, you'll find her office. Okay? Just ask at the desk. They'll tell you. If you're over on the Birmingham campus, Miss Janine McCoy-Jones, there's her phone number, and you can bring her stuff to her. You can visit the college website, request a meeting online. There's lots of things you can do. Okay? So please do it. Okay? Okay. Here is the college calendar, I would say. It says course calendar, but it's college. This is all on the website. This is academic calendar. I pulled this directly off of there. See, we've already lost one day for Memorial Day. We'll lose another day for Independence Day. Now I'm talking all this time. I need to move on. Any questions? Oh, okay. And then once you've read this, I'm going to go back and change. What was that? I was going to change. What's that? The what?
About the final.
The final, yeah. I'm going to change that, and once I have it changed, then if you'll either print this page and sign it and date it, or type it in and email it to me. Whatever you want to do, just let me know. And again, look at that. They got into plagiarism again. They're really on to plagiarism. Okay. Okay. Any questions on the syllabus? Okay. All right. Since we're through with that, let me close that out. And let's go to research paper. I'll try to do this more quickly if I can't. I just run my yap too much. Okay. I'll try to hit the high point. You choose your topic. Try to pick out a topic this week if possible. Okay? Go through the book. Go through other things. Anything to do with calculus. A person, theory, phenomenon, application. I love applications. If it has to do with your major or just an interest of yours, fine. Find a way that uses calculus. Fine. Go with it. Now here's another thing. A demonstration or an internet application that you find useful. Like I said, I've had students turn in things and said, boy, I found this website really helpful. It explained things much better than the book did, and certainly better than you did. Oh, no, okay, you can say that. I don't get hurt feelings. Okay, but if you find something like that, then you can write on that. Okay, so you pick anything. Okay, now I only want at least one, two or more or better outside sources. This is not an outside source. This is a source for ideas on what to write on, but your sources have to come outside the book. There are blurbs about people and about theorems and other things in here, little historical perspectives and background stuff. Yeah, that may give you an idea, but you have to get your sources outside the book. Okay? And anything you can find in the library and any good stuff you find on the internet. Unfortunately, at least half the stuff on the internet is total garbage. So be careful if you're using the internet. Okay? Textbook is not an outside source. I only want at least one word process page of text. Now, that may be a little fuzzy to you. What do I count a page of text? Well, some of you like to have, and it's fine with me, I don't have anything against it, some sort of header at the top, and then you skip a few lines, and you have your title, and you triple space, and then you start typing right here. What's one page of text? It's going to go to the bottom of that page, and then on a second piece of paper, come down from the top and go at least that far. That's a page of text. I've had some people try to just fill up the page with as much mess as you can and only have a little bit written and call it a page of text. No. I want at least one page of text. It's going to be at least two pieces of paper, but at least one page of text. Now, try to keep it less than 2 pages if you can, but if you get so fired up about your topic and you love what you're doing and stuff, and you just can't find a place to stop any sooner, I don't count off if it's too long. Directly, anyway. And I will count off if it's too short. If it's not that one page of text, I hold it up to the light, make sure it goes down that far. I do all that. Okay. I do count off if it's too short. But don't do this. I've only had, and like I said, I've been here 20-some years. And I've only been assigning these papers, say, 15 or 18 or so of those years. But I do it for all my classes, and I teach every term. I've never missed a term, and I've always had, this term I have 6 classes. I've had up to 8 classes in a term, so I've read a lot of papers. This is about average size of my classes, so I've read a lot of papers, and I've only had this happen 2 or 3 times I can remember. That someone decides to exchange quantity for quality. And they said, well, he said I could make it longer. He's not going to count off, so I'm just going to give him more and more of this stuff because I don't really, maybe I'm copying, I don't know what. But anyway, don't do that, okay? Because here's how I grade your papers. You turn it in to me, I count it. When it comes into me, it's a 100-point paper. And then as I start reading it, I will read every one of them. You start losing points if you have errors or other things in there. So if you turn in a cruddy paper, but a really long cruddy paper, you're going to be losing more and more and more points. So go for quality. Quantity is fine as long as it's good quality. If it's a good paper, you're not going to lose many points anyway, no matter how long it is. But if it's a lousy paper, don't just drag it on and on and on. Do a good paper. Okay. Double space. This is single space. I want your paper to be double space so I have more room to make notes and things like that. Standard pitch. This is 12 pitch. Too small, I can't read. Too big, I don't want to see that either. You can use any font that's readable. Okay. I don't care what format you use. MLA is what most English classes teach. APA is one that a lot of science and social sciences use a lot. I don't care. The main thing is be consistent, okay? If you start blocking your paragraphs, block all your paragraphs. If you start indenting your paragraphs, indent them all at the same place. I've had some indented here, here, and then this one will be over here. What's going on there? I don't know. Probably Microsoft Word is wacko. I don't like it at all. I use WordPerfect, but y'all can't read that. Okay. I mean, I can't send it to you. Okay. I count off for all the standard English stuff, like spelling, grammar, sentence structure, other types of errors like that. But so please, use spell check, use grammar check, good proofreading. It's all there on your word processing packages. But I also count off if you have the content off. Because most of the things you're going to choose to write on, I'll be somewhat familiar with. And if you're telling me something that's totally not true, I'll probably recognize it. So make sure you don't go to some of those sites on the internet. Okay, now when is it due? The last day of class, not the last day of finals, the last day of class. We meet as a class. But please don't wait till then to turn it in. Okay? You'll never have more time to work on this paper than you do right now. Any of you have tests already scheduled? Probably not. A few weeks into the term, you're probably going to have tests. You're probably going to have projects. You're probably going to have other things. So get started early. That's why I want you to get your paper topic. You can change your paper topic if you want to, but please give me something this week. Okay? By the way, on that, write your name on a piece of paper and the paper topic. And let me say this. This has nothing to do with the research paper. Because that's just 2 items on a whole piece of paper. Here's something else you can write if you want to. And the reason is, it doesn't happen often, but every now and then. In fact, I don't think it happened at all last term. I don't remember last time it happened, but it does happen periodically. I'll get a panicky phone call, or actually people come into my classroom door and say, "Thus and so is in your blah, blah, blah class. Do you have a good number for them? The ones in the system are not working." Someone's needing to get in touch with you, and they need to have a good number. Now, most of you probably filled out your paperwork correctly. But guess what? Some clerk had to transcribe that from your written thing to the system. And they may have just reversed 2 numbers. But they don't know which numbers they reversed. So occasionally they'll need that. So if you want to give me your very best phone number, you can. If you don't want to give it to me, you don't have to. Okay? Now, I'm guessing most of you that'll be a cell phone, right? And if there's a chance that that cell phone could have been left at home, the battery died, it got run over by a car, you left it in the car, any of those kinds of things, and you can't, if you want to give me your best backup number, like Mama's landline or whatever, you can give me that. And some of you may work. I don't know. You may work Tuesday, Thursday, and have classes Monday, Wednesday. I don't know. A lot of times that happens. And sometimes you can't use your cell phone at work. A lot of businesses don't want that. If you want to give me your number at work, if you can receive emergency phone calls there, you can give me that. So you can give me 0 numbers, 1, 2, up to 3 numbers. It's up to you. I don't care. Okay? So please do that. I just remembered to say that up here. Okay. Due by the last day of class. Get it in sooner. Here is the stick. If you turn it in after the last day of class, you start losing points. Here's the carrot. If you turn it in the month of May, which you only have today and tomorrow. Okay, sorry. If I'd have met with you Monday, this would have been on there. You can, if I receive it in the month of May, you get 3 bonus points. The month of June, 2 bonus points. The first 3 weeks in July, 1 bonus point, and the last week in July is the last week of class. If you wait till then, there's no bonus points. You just get your score. Okay? So, one more little thing, and most people don't request this, but I do. When you submit your paper, please attach a single page from one of your sources. Let's say you had 3 sources, pick one. I don't care which one. And then print me or copy me a single page from that source. 1 page. I want to see exactly. It may be something I can use later or something else. But do. Now, if you are writing on a computer application and that doesn't have a source, then give me the link to that computer application. Okay? But otherwise, print me a page. Any questions? Okay? This is out there on Blackboard right now. But now you've heard me talk about it. It'll be out there when I upload this to YouTube, all that I'm saying. So I'm going to leave this up here because I'm going to do it in my next class too. Are any of you in both classes? Sometimes transient students will take both. I don't know why, but we have no control over you. We have our Lawson students, but not transients. So let me get my locator card. Now, this is basically, you've gotten the information before. The summer 2018, my name, my phone number, and there's my email address. My department is mathematics, and here is my work schedule. They call it locator card because we put it on the door so the students can locate us. Sort of a dumb name, but anyway. I'm usually here at 7:45 every morning, Fridays for this week and the first week in August, but after that not, okay? Off campus on Saturdays, most Saturdays, and I've got 8 o'clock classes, Monday through Thursday. Monday and Wednesday, of course, is this class, 2 hours and 40 minutes, both days, and I've got a 20-minute, well, actually, I put down 15 because I didn't have the 40 in here. Actually, it's probably less than 15, where I swap out books or pick up more material, whatever. And then I have how to, okay? And that's in this classroom also. It goes right up until 1:40. That's when I get to eat lunch on Mondays and Wednesdays, okay? And by the way, I bring my lunch, I eat in my office, so you can come see me during lunch as well. Okay. I guess I should finish this. Okay. So I allow myself an hour lunch from 1:45 to 2:45, but guess what? You can come see me then too. I'm in the office advising from 2:45 until 6 o'clock. 6 o'clock, I'm leaving, okay? Or as soon after 6 as I can. I seldom will leave early, but quite often here later, okay? That's Mondays and Wednesdays. Now, Tuesday, Thursday, not quite as nice, okay? Because I already mentioned it to you, I have okay. Here at 7:45, but then an hour and 50-minute differential equations class, 10-minute break, hour and 50-minute linear algebra class, 10-minute break, an hour and 50-minute physical science class with lab, so that's another hour and a half on that. So I don't finish that one until 3:30, and then from 3:30 to 4, I'm on the road to Birmingham. So basically no office hours there. Okay, have to go swap out my book, stuff, and then I'm rushing there. I'm on the Birmingham East Campus from 4 to 5:30. But then I have office hours for that last half hour there. That's Tuesday and Thursday. And Fridays, I'm on the Birmingham campus. This is only this Friday and the Friday in August on the Birmingham West Campus Academic Building, be 122. This will be the month of May, the 1st of June, and the only Friday in August. And I'm there from 7:45 until 11:45. And I don't really eat lunch, but I had to put it in. They want me to. By the way, you'll don't notice there is no lunch on Tuesday and Thursday listed. I grabbed that 10 minutes between classes. I'm also cramming my face. Okay. Yesterday it was a cheese stick, string cheese, or something like that. In that 10 minutes, or an apple, or a sandwich, or whatever. And when I'm driving to Birmingham, I'm also cramming my face. Okay. That's lunch on those days, so you don't see it. So I have put it down 11 to 11:45. It's not really a lunch hour. I usually eat a snack and then I'll get on home. And I usually am there past 11:45, by the way. So any questions on that? Okay, that's also out there under, what do they call that? Class handouts and more. Okay. Now, what I need to do now, yuck, I got to close these out. I just remembered. I'll have to load them again next time, because I need to replace this flash drive with a different flash drive, which is the one that has okay. All right, if you got your text, which a few of you do, you'll notice there is a chapter P. That means preliminary. That's basically a review of pre-calculus algebra and trig. Okay? Did Mr. Rossi point that out to you and ask you to review that? And she told me that she was going to send me, maybe she has, I just haven't seen it, something on the London Ferris wheel and how that is mapped by the a sine function or a cosine function. If I find it, I'll send it to you. You won't need it. But it's not a bad idea to look through this, because I turned to the first page in that, because I don't usually do it. There's a person right on the very first page, page 2, René Descartes. Potential paper topic, it's in your book. Cartesian coordinate system, that's where it gets its name. That's a potential paper topic. So you can look through here. If there's anything you're fuzzy on, you're not sure about, you won't have a question about, please ask. So go through the P chapter. We're starting the class in chapter 1. And this starts with, I thought it clicked, but it didn't. Okay, why is it not opening? This, last night, when I was working on this, I very frequently had to go and go into Task Manager, and everything seems to be working, and then when I go out, things will open. You're supposed to do that now. Weren't you paying attention? It's not. So what I think I have to do is get out of it and bring it back up again. Sorry about this. Except it's not letting me get out of it. So I'm going to go back to the Task Manager and get out of it this way. and now it'll open up and then shut down. Well, it's not doing anything here either. Okay, let me try it again from here. Ah, it's doing something this time. Did it do that last time? I didn't notice if it did. This should have nothing to do with the Wi-Fi system. Is that up or still down? What were you going to say?
The problems that we do in the book, are those going to be problems that we turn into you? Or
Okay. Oh, yeah. Homework type stuff?
Yeah.
Okay. Only if you need to. That's not like a weird answer. If you can't figure out how to get the answer in the back and you feel like you're doing something systemically wrong but you can't figure out what that is, yeah, turn it in to me, and rather I have it with you, say, during my office hours, and we go through it and figure it out. But if you can't be here during office hours and you want me to look at it and see if I can figure out where you're making your mistake, I'll be glad to do that. But no, if you're getting them right, you're understanding it, I don't need to see it. That's your practice preparing you for the test, okay? So that's for your benefit, not my benefit, okay? But I'm happy when you make good on the test, but it's mostly for your benefit, okay? And this is still not opening. So what I'm going to try to do is shut down the whole thing here. Ah, there it is. Okay. I knew I had to do something to Yankees thing. Is that a stretch or a question? Okay. All right. Okay, chapter 1 is limits and their properties. Okay. Section 1.1 is a preview of calculus. Okay. Let's get through this in a hurry if we can. The objectives here is to understand what calculus is, how it compares with pre-calculus, understand that the tangent line problem is basic to calculus, and understand that the area problem is also basic to calculus. Okay? Let's go through this in a hurry. What is calculus? Anyone have an idea? What is calculus?
Like, these people are doing lots of pre-calculus, but he's going a step forward.
Okay?
Like,
Building on pre-calculus, going a step further. Why is calculus there anyway? Anyone know? We may be hitting this.
To give us headaches.
What?
To give us headaches.
Give us headaches? Okay. Only if you're prone that way. Okay. Actually, a good old guy named Isaac Newton. This is my best understanding. I may be a little off on it, but I think this is what happened. There was a colleague of his, and Isaac Newton was one of the most brilliant minds I think this world has ever produced. Okay? And a colleague of his, I believe he was about the same time, was, I always go blank on this guy's name. He did the laws of planetary motion. Goodness! Right there, but I can't quite grasp it. And he came up with a description of planetary motion, that the planets were not traveling in circular orbits, but elliptical orbits. Because the astronomers had noted things were in a really regular pattern, except not regular enough, okay? And this guy, I know you're looking it up, I hope you get it, came up with a description that the planets travel in elliptical orbits, not circular orbits. Close to circular, but not quite. Kepler's laws of planetary motion. Very good. Okay? I think he lived about the same time. Well, Kepler, great mathematician, okay, and he could see that these things were true. There were three laws. One, that they followed elliptical orbits. Number two, that the area that they travel from one, there's a focus here, area that they traveled in a period was always the same, even though the distance was not the same, okay? That was rather bizarre. And then there was a relationship between the semi-major axis and this kind of stuff. He came up with this stuff empirically, by studying the data. And boy, how he did this back in that time, I don't know. He came up with these 3 laws of planetary motion that described and explained all the things no one had ever figured out. But he said, I don't know why these are true, but they just seem to work. And I think he went and asked Newton how this could work. Well, all we had at that time was algebra, okay? Mathematics and algebra, trigonometry, geometry, but they could not, Newton needed something that gave him not average speed, but instantaneous speed. He needed to be able to measure the area. He didn't have anything. They had approximations, all this kind of stuff. So he came up with the concept of using incremental changes to be able to come up with instantaneous speed and instantaneous and area covered and that kind of stuff. So calculus is the mathematics of change. It deals with not just what goes on the average. If I said I'm driving from here to Tuscaloosa, sorry, I just choose that because it's nearby. Okay, you have all the okay, all right. But you know, if I were, and I said I'm going, you know, take me an hour to get there. How far is it? 60 miles? I don't know. Whatever the distance is, it's going to be 60 miles an hour. Well, guess what? That's going to be average speed. I'm not driving 60 miles an hour when I leave the parking lot. I better not be. Nor will I be 60 miles an hour when I'm on the expressway. I better be closer to 70, but it's an average speed. But Newton needed to know instantaneous. What is it at any given moment? You couldn't do that with algebra, geometry, trigonometry, nothing like that. So calculus is the mathematics of velocities, accelerations, tangent lines, slopes, areas, volumes, arc lengths, centroids, curvature, all these things that you cannot do with just algebra. Okay? So like you said, you have pre-calculus algebra that builds toward it, that enables us to do this. Okay? These variety of other concepts that have enabled now scientists, engineers, economists, all sorts of people, medical applications, to deal with things that are in real time. Okay? Instantaneous. Real life situations. Although pre-calculus mathematics deals with velocities, accelerations, tangent lines, slopes, and so on, there's always it's average. It's not instantaneous. A fundamental difference between pre-calculus mathematics and calculus. Pre-calculus mathematics deals with average. This deals with instantaneous. Pre-calculus is more static, whereas calculus is dynamic. Okay? Guess what? The world is moving at a faster and faster pace all the time. We can't have static solutions to really dynamic problems. Here are some examples. An object traveling at a constant velocity can be analyzed with pre-calculus mathematics, no sweat. So once you're on cruise control, pre-calculus algebra gives you all the answers you need. But before and after, you not, okay? To analyze velocity of an accelerating object, you need calculus. If it's changing speed, you can come up with average velocity, but you can't have instantaneous velocity. The slope of a line can be analyzed with pre-calculus mathematics if you have 2 points on the line. But if you only have 1 point, the slope of a line that's tangent to the curve, not between the curve, but tangent, how can you do that with algebra? You can't. To analyze the slope of a curve instantaneously with just a tangent point, 1 point, you need calculus. Can't do it with pre-calculus algebra. Curvature of a circle is constant. Can be analyzed with pre-calculus mathematics, but to have variable curvature, for instance, the ellipses of the thing, they're changing constantly. You need calculus. The area of a rectangle. Pre-calculus, no sweat. Length times width, you got it, okay? That analyze the area under a general curve, as in the area swept by that planet going around the sun. The area there, no way you can do that with algebra, okay? Pre-calculus mathematics. Okay, each of those situations involves the same general strategy. You have to reformulate what you're doing in algebra, pre-calculus math, through the use of a tiny, tiny, tiny little differential and make it instantaneous. Okay, that's where a limit comes into play. And that's what we're doing in this chapter. So one way to answer the question, what is calculus, is say calculus is a limit machine. Okay, fine, cute, but I really don't like them so much, but yeah, they're necessary. That involves 3 stages. First stage, pre-calculus mathematics, such as the slope of a line, the area of a rectangle. Yeah, we understand that. Second stage is the limit process. The third stage is the new calculus formulation, such as the derivative or the integral. When you talk about slopes of tangent lines, you're dealing with derivatives. When you talk about area under a curve, that's integrals. So the limit process is sort of the connecting link between pre-calculus math and calculus. So that's why we start with that. Here are some familiar pre-calculus concepts coupled with their calculus counterparts. Okay, without calculus, what's the value of f of x when x is equal to c? Well, you just plug it in and see what it is, okay? For there. But what if f of x is not defined at c, but you want to know what it's approaching as you get closer and closer to c? Okay? Then you need calculus, the limit process. Slope of a line. If you know a change of y and a change of x, yeah, you can calculate the slope. Slope is equal to y2 minus y1 over x2 minus y1. Rise over run. We know that from a long time back. What if you have the slope of a curve where there is no 2 points on it? You only have 1 point. There you need a dy by dx. Okay? Where d is infinitesimally small. dy and dx. Okay? That is not a dy, that's not a dx. That would be so small you can't even see it. But that's a general concept. Secant line to a curve, yes, we know that. The average speed, if you're at this point here and then that point there, average speed was change of displacement over change of time. Okay? But if you want the instantaneous speed at that point right there, just like up here, you let your dy get smaller, your dx get smaller, tiny, 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 until you get it. That's a limit process. The average rate of change between t equal a and t equal b, again, that's sort of like just what we're talking about, driving here to Tuscaloosa or here to Birmingham or wherever. Then you average is how far you travel divided by the change of time. Here, the instantaneous rate, this is sort of like using your odometer and your watch to say what your average speed was. This is like using your speedometer to see what it is at any instant. That's incremental, instantaneous. Okay. Curvature of a circle, everybody knows what that is, or you will if you don't. But curvature of a curve, at some particular point, that's changing constantly. Here the curvature is huge, here the curvature is quite small, that's even smaller. This is in between, So there you need calculus. Height of a curve, x equals c, maximum height of a curve on an integral, okay? You got to have calculus for that. This can be done with pre-calculus. Tangent line to a sphere, or tangent plane to a sphere. Yeah, maybe you can get that in pre-calculus algebra. We never did. But tangent plane to a surface that's not a sphere, yeah, you can do that with calculus. Direction of motion along the line, yeah, as long as it's not changing, you got that. The direction of motion, in other words, what's the slope of the tangent line again? At any point on that line, you need calculus. Goodness gracious. Area of a rectangle, yeah, you can do that. Area under a curve, no way to do that without calculus. You can estimate it without it, but no way to get it for sure. Work done by a constant force, yeah, force times displacement. Work done by a variable force, the integral of force times your your incremental displacement. Center of a rectangle, yeah, just draw the 2 diagonals, you got it. Centroid of a region, that takes calculus. No way without it. Length of a line segment, yeah, you can measure that almost, There's a distance formula, gives that exactly. But the length of an arc, no way you can do that without increments. Doing calculus. Goodness gracious, and more of these. Surface area of a cylinder, yeah, you can figure that. There's a real neat way to do it. Imagine you cut a line down there, unfold it, you have a rectangle. length times the area of the circumference of the circle. Pretty easy. Surface area of a solid of revolution that looks like that, got to have calculus. Mass of a solid of constant density, yeah, if you got the solid, you can calculate the volume, you got it. But mass of a volume with variable density, it's lighter on this end, heavier on that end, you got to have calculus for that. Volume of a rectangular solid, yeah, length times width times height, no problem. Volume of a surface under a curve, you have to have calculus. Sum of finite number of terms, yes, you can add those up, even using a calculator, okay? But sum of an infinite number of terms, you got to have calculus for that. That's getting into Cal 2, by the way. Some of this was Cal 2. So let's look first at the tangent line problem. When I taught this course last time, I don't remember all this, but maybe it just blew it off in my mind because I don't really care for it that much. Notion of limit is fundamental to the study of calculus. What do we mean by that? The following brief descriptions of two classic problems in calculus. Tangent line problem, the area problem. Should give you, an idea of the way limits are used in calculus. All right, here we have. The tangent line problem, you are given a function f, there's a graph of f, and you're given a point on f. There's the point. It could have been here, it could have been here, it could have been anywhere on that curve, okay? And you're asked to find an equation to the tangent line of the graph at that point P. Well, you can find an equation of a line if you know 2 points, or if you know 1 point and the slope. But how can you find an equation of a line if all you have is 1 point? Okay? 1 point. You need to know the slope. If you knew the slope, you can give the equation of a tangent line. But you can't get the slope without 2 points, okay? Now, if this was a straight line, right at mx plus b, m's your slope. But this is a constantly changing curve. The slope is changing all the way. Here it's negative, there it's 0, there it's positive, there it's more positive, okay? How are we going to determine what the slope is at that point P?
Secant lines.
Say again?
Secant lines. Secant lines.
The secant line. Okay, you're absolutely right. There is a secant line here that has that same slope. But how do you figure out what points it intersects? So that's the issue. And we are going to use the secant line and the limit of the slope of the secant line as those 2 points get closer and closer together. That's exactly where we're going here. Okay? So that's what comes up next. Except for cases involving a vertical tangent line, hey, you can't go there, okay? The problem of finding a tangent line at any point P is equivalent to finding the slope of the tangent line at any point P. Because once you know the slope and 1 point, you got the line, okay? You can approximate the slope, just like you said, by using a line through the point of tangency and some second point. So here's the one we're interested in, P. Pick another point on that curve, okay? Now this is a different curve from the one they had before. But here's Q. Now how is Q different? P is at C, alpha C, that's the point P. This value x equals C, and where x equals C, the y value is alpha C, okay? Because y is equal to alpha of x, right? So C, the value of y at C is alpha C. Now, up here you've increased x by some amount, delta x. So your x was C, and you increase that by delta x, so you got C plus delta x. So that's your x value for that point. Your y value is f of C plus delta x. You just take the f function and plug in C plus delta x here. Okay? So there is the point C, the point Q. Okay, now, to get the slope of this secant line is change of y over change of x, rise over run. So alpha C plus delta x minus alpha C. That's going to give you the length of that line, right? And x plus, or C plus delta x minus C, it's just going to be delta x. There's that line. So the slope of this secant line is rise over run. Alpha c plus delta x minus alpha c divided by delta x. Well, that still doesn't give you a tangent line. Here's what we're going to do. We're going to let delta x shrink. That means you're coming down the curve. Your new q is going to be a little bit closer. And that secant line is going to have a slightly different slope. You got to get closer, slightly different slope. You got to get closer, slightly different slope. You got to get as close as we possibly can. As long as you have a delta x, you're going to get really close to the slope of that tangent line. You won't get there until you let delta x approach 0. But guess what? You can't divide by 0, can you? So that's where calculus comes into play. This is the secant line. I've jumped ahead. The point P, alpha c, and Q is this one. I've already talked about that. So your slope of that secant line is the difference of these two over the difference of these two, but you see the c's cancel out, so that's what your slope of the secant line is. So to get the slope of the tangent line, and here's what I was saying, let your q's get closer and closer to P, and you see the secant line here, 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 and it's getting closer and closer to the slope. That's a pretty serious thunder. Are we still under the effect of Alberta, or is this a different system? It's been a pretty rain-producing storm, okay, and a lot of thunder today. We didn't have that yesterday that I recall, okay? Now, what the deal is here, you're letting the Q get closer and closer to P, which basically means your delta x is getting smaller and smaller and smaller. As Q approaches P, the secant lines approach the tangent line. When such a limiting position exists, then the slope of the tangent line is the limit of the slope of the secant line. We already have that formula for the slope of a secant line, and that's it. So basically, we do the limit of this expression, that's the slope of the secant line, as delta x is closer and closer to 0. You can't ever get to 0. You can't divide by 0, but you get the limit. Rise over run, it always works as long as it's a finite difference. What we are going to go to is what if the delta x is approaching 0 and it no longer is finite. Okay. They left you hanging. Sorry about that. We'll get there. Let's talk about the area problem. Second classic problem in calculus is finding the area of the plane region that is bounded by the graphs of functions. Okay? That problem can also be solved with a limit process. In this case, the limit process is applied to the area of a rectangle to find the area of a general region. Here's what we mean by that. Here is a curve. Y is equal alpha of x. That's where we always start. Okay? And what we want is the area of this paint between x equal a and x equal b. Well, we know the length of this, but boy, the height is variable, right? How in the world are we going to get the area under that thing? Okay? Here's the trick. Let's draw little rectangles under that. Okay? We'll start with big rectangles. We'll split A to B into 4 pieces and have 1/4 way here, halfway there, 3/4 there, and all the way there. And then we do these areas of rectangles. And what they chose here is to use the left-hand edge and use that as the area. Okay? So this will be length times width, length times width, length times width, and length times width. Well, this underestimates, this under and over a little bit, mostly under, this overestimates, but this underestimates. So we know we're too small there. But we got an estimate, okay? Now, you might say, well, why didn't we take the right-hand limit? You could do that, okay? Then it would have been here. This one would be overestimating, this would be underestimating, this would be about the same, and this would be overestimating again. Well, you might say, why don't you average those two? Well, that's going to give you pretty close, but it's still not exact. Another thing you could do, rather than going through all that trouble, is make your rectangles smaller. And now you have less underestimate and less overestimate, okay? So you've gotten a better job, okay? Well, if you did that, let's divide again and get smaller and smaller rectangles. Well, what are your rectangles? That's going to be a dx, isn't it? Change of x. And it's uniform between the 2 points. So again, we're going to have to deal with a smaller and smaller. And when you get that small enough, you really are very, very, very close to the area under the rectangle. As you increase the number of rectangles, you're also decreasing the width of those rectangles. The approximation tends to become better and better and better because the amount of the area missed by the rectangles decreases every time you do it. Your goal is to determine the limit of those sums of the areas of the rectangles as the number of rectangles increases without bound. As the number of rectangles increases, your width is decreasing without bound. Or no, with a limit of 0. Whoa. Okay. That was section 1.1. A lot of blah, 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 by the way. Okay? There is one person mentioned in there, Grace Chisholm Young, and she did a lot of the work. This is in the 1900s, 1914 and 1916. She did a lot of work in calculus that I'm not sure many people will recognize her. She actually won the Gamble Prize from Girton College. I'm not even sure what that is. But there's 1.1. Now, exercises in this is a lot of talking, no real problems in this thing. If you want to take a look at them, you can do any of the odds. Well, number 1, it's a concept check. It's just asking you to do something. Number 3, by the way, if you got your text, you'll see number 3 is in red. The number 3 is red. That means it's at calcview.com. Okay? Find the distance traveled in 15 seconds by an object traveling at constant velocity. You know how to do that. It's pretty simple. Number 5 is another rate of change, and you can play around with that one if you want. 7, 9, so very few problems. 3 through 9, any of those odds, all the odds, and by the way, you'll notice this at the top. See calcchat.com for the tutorial help and worked out solutions for the odd number exercises. So you can do any of 3 through 9, but if you do number 3, you can find that more detail at calcview.com. Okay? And guess what? This book is really on top of things. All these at calcview.com, all you have to do is get your smartphone and click on that, and you'll go straight to it. You don't even have to type it in. So the calcview.com has, what do you call these? I call them square. Second. Someone said it.
I'm going to say QR codes.
Huh?
QR codes.
QR code, right? Is that what you said?
Yes.
Yeah, my wife has to tell me every time because I always forget. I call them square barcodes, okay? That's not what they are, but it's a QR code. Okay. You can just click on that and see it. So let's move on to, that's not what I want to do. That's what I want to do. Okay. 1.2. All right. Does anyone need a bladder break? Let's see. What is it? Yeah, I could kind of use one, and it's sort of a decent place to have it. You want to take a quick break? Okay. Start on 1.2. Let's quickly go over safety. There's nothing we're going to be doing that is a really big safety hazard, but it is something we need to have in mind. What are some issues we might need to think about in terms of safety? Second? Tornado or weather. Okay? Tornadoes, severe thunderstorms, stuff like that. We heard that thunder earlier, That should have clued me in. I forgot about this, but especially tornadoes. And guess what? This is just a simple tropical system that came through. And look at what we got out of it. If this was really a really powerful hurricane, I can remember Ivan a few years ago, that by the time it got to Birmingham, it was still a tropical storm, probably as strong as this one was when it hit the Gulf Coast. So that was pretty serious. And it did spawn some tornadoes. So what do we do if we hear that siren go off? What's the procedure? What's the plan? Oh, tornado coming, I gotta get home and get the dog in, right? No. Okay? Worst place to be when the tornado is in the area is on the road. That car is not at all any good whatsoever. So what do we do? Okay. The hall is a good idea. Which hall is even a better thing? What? Let me get closer to my microphone so this gets recorded. The general concept is to go low and interior. Remember that. Low and interior. So where would we go from here? We're on the second floor. We need to get down to the first floor. Okay? So we go out the door here. Here we are in this corner classroom here. Go out the door, hang a left, go down the short half flight of stairs here, hang an immediate left, go down one more full flight. Now you're on just about as low as you can go in this building. Okay? You're on the first floor, directly underneath here. This is just second floor. Directly in front of you there, you'll see two restrooms, just like we have on the second floor here. And actually, those are not bad places to be. And here's why. The walls are relatively close together, just like the hall, okay, that Daniel said. Even closer, and guess what? Lots of corners. Because your greatest strength is in a corner. You have strength this way and this way, okay? Close walls, greater strength. So the restrooms are not bad. Two little problems with them. You may not want to hang out in the restroom indefinitely, you know, that's not the best place to be sometimes. But number two, there's no emergency lighting in there. And just like we've seen all this lightning and stuff, if we had a tornado, a really good chance power is going to go off. And so therefore the restroom may not be the most pleasant place to be. Well, right next to the restroom is what it says corridor here. Downstairs is the academic dean's office. She very seldom is over here on this campus, but sometimes the associate dean is over here. But especially in the summertime, the guy who does the summer enrichment program for the high school students, when they're on this campus, he uses that office. So that office will occasionally be open, and if they invite you in, again, close walls, corners, safe. Here's the other thing about the restrooms and that, and all along here. The back side of this wall here down on the first floor is below ground level. In other words, you got soil back here. Not up here, but down there you do. So therefore, there's not going to be anything knocking those walls down. So that back wall is a very, very safe area. Of course, that's where our office is. Okay. Now, next to that is a classroom. And the classroom, big open space. I wouldn't congregate in the middle. Stay near the wall, especially the back wall. It's going to be pretty safe. And the corners are very safe. All the walls are pretty good, strong walls, concrete block walls. So they're probably not going to tumble. But in the middle, you may have some issues there. Okay? Then you go through some glass doors that separate that part of the building from the library. And the library, just inside it on the right, is a computer lab, which is smaller than the classroom, so the walls are closer, safer, and you still got the corners. Okay? Right next to that is a little bit bigger room, not as big as the classroom, but bigger than the computer room. That's what I call the reference room. Okay? That's where your globes are, your atlases, and other things you don't really check out, you just use. Okay? And that's not a bad thing, especially the back wall, because it's up against soil. Okay? Don't go any further in the library, because then you're on an exterior wall. You do not want to be on an exterior wall. And the one place I didn't mention, but Daniel mentioned, was the hallway. That hallway is really one of the best places to be. The walls are relatively close together. The trouble is there's not many corners, okay? But they do have emergency lighting. So if the power goes out, you'll have light in the hallway. You won't in those classrooms or offices or other things. when you go down there, I'm going to be the last one out of the room. Now, all of you look pretty healthy and able-bodied right now, but let's say somebody over a weekend goes and plays basketball or something, twists a knee or hurts a foot or something, and you're sort of hobbling around. I'm going to be helping that slowest person out of the room and making sure that person gets downstairs as well as everybody else. So the rest of you have already gone. You've been going not super slow, but you've been going carefully, moving along, but not rushing, not tripping, not falling, going down, getting down there. When I go down, in addition to helping them, I'm carrying my roll book. So once I get down there, I'll be calling roll. We have to account for everybody. So that means if you decide to, whoa, no more classes today, I'm out of here. No, don't do that. Not safe for you to be there. And guess what? I get down there, can't account for you. I've got to go back and look for you. Or somebody does. Risking life and limb, because that tornado could throw a limb right through the window when I'm checking out the classroom. That's why we want to get out of here. So hang together. When I get down there with that last person, call the roll, account for everybody. Then if you want to go mix and mingle with friends or whatever, find a place to snooze, whatever you can do, okay? You might not like the emergency lighting. You want to go someplace dark and safe. Okay, so there's weather emergency. What other kind of emergency do we have?
School sheet.
Say again?
School sheet.
Okay, unfortunately, we have to talk about these days too. Back in the earlier years, never even would cross my mind. Now they're happening with such frequency, we have to think of what to do. What do we do in case, now guess what? I'm hard of hearing. If there is a shooting going on, you're probably going to hear it before I will. Okay, if you hear something and detect that, what do we do? What are the things you have to have your mental step checklist to do? Any ideas?
Tell you.
Say again? Tell me. Yeah, okay, I didn't hear it. Say, that sounds like gunfire. So what do you reckon I'm going to do?
Barricade the door.
Okay, okay. Now, fortunately, I have a key to this door. Okay? So I can lock the door. The sad news is there's no way to lock it from the inside. In fact, there's not even a button you can push from the outside. I mean, from in here. I have to go around to the outside and physically lock the door. Don't pull it to until I get in, okay? But anyway, then I come back in, okay? Now, what y'all are doing meanwhile is be very quiet, turning all your phones to silent or vibrate or something so nobody can hear it if they ring, and you get right back to it. See, here, he can look in. Most of the time it's either a couple of times it's been cheese, but most of the time he look in, fire through here, or even fire through the wood. Might make it. Not going to make it very well fired through concrete. But there's another issue. We have another door to the classroom. Here's an office here. Here's an office here. Here's a classroom over here. And it has a door to the outside. I don't have a key to that door, so I can't lock it. I'll go close that door, turn off the light, okay? Light, and you'll not be able to come in here, because it's not here. Usually nobody here, okay? Now, what you might say, well, why don't we just lock this door? I do have a key to this door. But guess what? And it has a button right here. I don't even have to go outside. I can push the button. It's locked from the inside, but not from the outside. That doesn't do us any good. He can still get in. We can't get out. So we don't want to lock this door. This door, nice solid door, but it has a deadbolt. I don't have a key for that. This door here, I don't have a key for, but it does have a button. I press this button. It's locked from the outside. This is the one we lock. Okay? Either I do it or you do it. Close that door, turn off the light, lock this door, close this door because you can see through the glass there. All the lights are off, we're very quiet. We'll close this door too, make it think it's locked or whatever. But we're over there and you can see it's open. Okay? So that's the procedure. Okay? And we get very quiet. We stay quiet back here where he can't see us and can't shoot us, and hope that we go through. If something happens and he does find a way in, I'll take the lead. Okay? Y'all have your future ahead of you. Most of my life is behind me, okay? So you don't be heroes. Let me do whatever I can to talk them out of it or whatever. But hopefully, we'll never have to go that far. Really hope we don't. Okay. So, any questions on active shooter? Now, in one of my other classes, one of the students said, you also could run if it's far enough away. But, you know, if there's, here the gunfire is pretty far off, unless you can tell which direction it is, you don't know which way to run. So I think the safest thing is to hide. If something happens, then we'll deal with that. But, okay. External weather, active shooter, what's another thing we might need to worry about? Fire, okay? Something inside the building. We'll have chemical spill or something like that too. Okay, let's take worst case scenario. The fire starts in here. My computer blows up and arcs and sparks and sets all those papers on fire, the books on fire, the desk on fire. What do we do?
Tell you.
Okay, yes, I've not noticed that. Okay, I understand. Thank you very much for that vote of confidence there. I'm hard of hearing, but I do, never mind. Okay. All right, what else do we do besides tell me? Again? Leave, I heard. Yes, let's get out of Dodge and let the building burn down and not tell another soul that the building's on fire. That sounds like a very...
Fire alarm.
Oh, fire alarm. That's a good idea. Where is the closest fire alarm? Anyone know?
Down the hall.
Okay. This is the old part of the building. Everything you see here, not this part down here, but everything that's up here on this level is old, built before fire alarms were required by code. Nothing on this hallway, that hallway is going to have a fire alarm. Nothing. So we have to go to a newer part of the building. And it's not too far away. Now, since you have to leave, I say let's have a buddy system. 2 people go. In case one, in a panic or people pushing or shoving, 2 is better than 1. So 2 people go. Where is the closest fire alarm? Well, we go out the door here, hang a left, go down this half flight of stairs, but then go up a little bit further to this corridor. This corridor here goes from the 2nd floor here to the 1st floor here. Not a single step went up or down, but this is the new part, and being a new part, as soon as you come to the double doors here, you'll have a fire extinguisher on this side and that side. Closest one, get to the floor. Okay? So we've sent somebody down to do the alarm. What else do we have to do? If the fire started in here. Say again? Okay, we are going to get out. But, say again, yeah, let somebody know. Now, the very best thing you can do is have on speed dial, and this is not just for these kind of emergencies, anything. If you get the Lawson Bessemer campus police number, you can go down to the police thing. I have it in my other grade book. I don't have it in this one. I meant to get it in this morning. I forgot it. Get the best number for the police. Have that on speed dial. That's what you would do. If you don't have that, 911. Because we need to let somebody know. We are doing the alarm, but we need to let somebody know where. Because the alarm doesn't tell anybody where. The police would not know where to go to look. Okay? So call the police or do 911 and let them know where it is. Okay? So that's the second. Still, one more thing. The thing is burning in this room. What might we want to do also? Put it out. How do we put it out? Fire extinguisher. Where's the closest fire extinguisher? Any ideas? Just right outside the door here. Within 5 feet of where I'm standing. There it is. Can't get much closer to the fire extinguisher than that. So somebody run out there and get the fire extinguisher. It could be me, but I know that some of you, all your life, you just thought, wow, how cool it would be to break that glass, right? Oh yeah, I could tell she was thinking that, okay? So someone go out there, get the fire extinguisher. I'll fight the fire if I need to. I don't want y'all to get damaged. Y'all just start getting out. Okay. And where do we go from there? Well, we don't go in the building. Not if the building might catch on fire. We go out of the building. Okay, so again, you go out the door, hang a left, go down the half flight of stairs, hang a left, go down one complete flight, but rather than going in, you go out. Okay? That's the closest exit to us. Right there, you go out. And when you go out, it's just down short ways from him. Now, you can't see much with all the leaves on the tree, but it's just right there. You can see the sidewalk going out and go perpendicular away from the building. Don't go along the building. The building's on fire, something explodes, you're going to get hit by glass. Get away from the building and go across the green grass here and go down to that parking lot. Okay? That's shown here in this illustration. Not a very good picture, but let me show you where we are. Here's the A building. We're in this classroom right here in the corner. We go down that stairwell, go out the building, and down to this parking lot right here. Everything from this end of the building goes to that parking lot. And that's where we go. You stay in the house. You don't say, hey, fire in the building, no more class today, I'm heading out of here. No, because, again, I'm the last one out. I've been fighting the fire if it was in here, or if we just hear the alarm. I'm helping that slowest person, make sure everybody get out. We get down there to the parking lot. I have my grade book with me. I call roll again. If you have taken off to go buddy around with a friend or get in the car and go home, we don't know where you are, then myself or some fire professional has to go back into the burning building looking for you, risking life and limb. Don't do that. Stay together. They'll let us know, usually pretty soon, what the plan is. And they may say, head on home. Or they may say, hey, we got rooms in the B building, the Ethel Hall building, let's move the class there. Okay? So hang around. That's not the reason. The reason is that nobody has to go and look. All right. Any questions? 3 things to keep in mind: safety. Think about them ahead of time so if it happens, you don't panic and freeze and not know what to do. Okay. Let's see if this opened. It's been really weird today. Well, I can't even get it to open. There it goes. All right. And we'll go from current slide. Still chapter 1, limits and their properties. Now we're going to, in section 1.2, finding limits graphically and numerically. Another big boo hiss, not my favorites, but it's good to get an idea of what's going on here. So our objectives here is to estimate a limit using a numerical or graphical approach. Usually pretty long. Okay. Learn the different ways that a limit can fail to exist. Okay. And we'll also study and use a formal definition of a limit, which is no picnic either, but it's okay. So let's do an introduction to limits here. We saw we needed them. Okay. If you were going to sketch the graph of this function, how would you go about doing that? Just tell me. If I said, sketch this function, what would be your process?
Find the domain.
Second?
Find the domain.
Okay, find the domain. Oh, good idea. What is the domain of that function?
What's not going to work?
Second?
What's not going to work?
Okay. Actually, the domain is what will work. You eliminate what won't work. What won't work is that?
0.
X equal 1.
1.
Yeah. If the denominator is 0, it's not going to work. And if x minus 1 is 0, that means, or x minus 1 cannot equal 0. Otherwise, that would be the domain. So add 1 to both sides. X cannot equal 1. Okay? For all values other than x equal 1, there's your domain. So that's the first thing they did too. Find the domain. Okay? So for all values other than that, you can use the standard curve sketching techniques. Like set up a t-table, x, y, x, f of x, plug in values except x equal 1. You can't do x equal 1. But plug in all the others, a bunch of others, and see if you can get a general idea of where that function is going. Okay? At x equal 1, however, it's not clear what to expect because it's not defined there. However, if any of you noticed, do you notice anything about that numerator and denominator? Do they have anything in common?
X.
Second?
X.
X? Well, yeah, they both have X's in them, but say again?
X minus 1.
You're absolutely right. You can factor that numerator. And does anyone remember how to factor a difference of 2 perfect cubes? That's what that is. Oh yeah, you remember that. I know you do. That was one of your favorite things in pre-cal, right? Or was it Math 100? Well, actually, take the cube root of the first, x, the cube root of the second, 1, and keep the same sign. X minus 1. Yep, there is something that is common. What's the rest of the factor, though? The second factor. Well, here, this is my technique. I don't know if you do it. Forget about everything else. Just take this, square the first term. That would be an x squared. And then the opposite of the product of the two cube roots. X plus 1. I mean, x times a positive 1. That would be plus x. X times 1 is x. So it would be, I'm sorry, I said square it and I didn't. Square the cube root of that, then plus x, the product of the two, but opposite sign, and then square the last term, plus 1. There you have it. Now you can multiply that through and see that you get that. I'll let you do that on your own. But now you can just notice the sound effects, you know, as you divided those out. All you have to do is plot this quadratic. Okay? That's easier than doing the dividing too. So plot that, pick points and do it. The only thing is you have to remember, even though you got rid of this, you don't get rid of the fact that it's not defined at x equal 1. So when you are plotting this, you can put a 1 in here. You get 1 plus 1 plus 1. That would be 3. But you know it can't be that because x cannot equal 1. So at 3, you put a hole in the graph. The rest of it looks just like a parabola, except you have a hole right over there at 3 because it's not defined. Okay? So that's what you do. Now, they aren't doing it that way. They're doing it numerically, okay? And what they're doing is a whole shebang there, x and f of x, and plugging in values. At x equal 1, you don't know what it is, okay? That's the unknown here. But you're plugging in 3/4 of 0.75, 0.9, 0.99, 0.999, and you can keep going as close as you want to. And you get at 3/4, you get 2.313, probably 2.3125 or something like that, but it's okay. 0.9, you get this. 0.99, you get that. 0.999, you get that. It's getting closer and closer to 3, which we got when you just plugged in when we factored. You can start 1 1/4 here, past that, 5/4, plug that in, or 1.25, you get this value. Similar to this, but not quite the same. Okay, it's just greater. Okay, 1.1, 1.01, 1.001. So this is 0.003 above. This is 0.003 less. Yeah, that's heading toward 3 from both the left and the right. But at 1, when it's going toward 3, you have to have a 0 there. I mean a circle there, a hole in the graph. Okay. So this is how you express it. Now, you could do it using the t-table. They did a horizontal t-table, and do that and plug in the values that way. Or, as we did, we factored it and then got this parabola, but knowing that you can't have a value x equals 3, x equal 1, 3. You know, so therefore put a hole there. And the rest of the curve looks just like that. Here was the limit as you're going approaching this way or that way. Had a limit of 3, but it has no value at 3. The limit of f of x as x approaches 1 is 3. And here's how we write it here. The limit of f of x as x approaches 1, that's got this counter underneath it, is 3. So the graph of f is a parabola, has a hole at the point 1, 3, shown in this figure. Although x cannot equal 1, you can move as close to 1 as you want to, and you'll get values. You just won't have any value at x equals 1. Okay? So this is how we write it, and get used to it. For all this chapter, we're going to be using that notation. Any question? Does it make sense? Okay. So this discussion leads to an informal definition of a limit. Not the formal one, but informal. If f of x becomes arbitrarily close to a single number L as x approaches C from either side. Okay? Either side, if it seems to have some limit, then we say the limit of f of x as x approaches C, x is going toward C, the f of x is going toward L. This is written this way. The limit as x approaches C, that's the independent variable, the horizontal variable is approaching some number on its line, then the f of x, the curve, whatever that happens to be, is approaching that value L. That would be the limit. So the limit in our other as x approached 1 was 3. Okay? So this is how we write it. Now that's an informal, just sort of warm and fuzzy feel for what's going on. Okay? Here's example 1. Evaluate the function f of x is equal x over 1 plus x over the square root of x plus 1 minus 1 at several values near 0 and use the results to estimate the limit. Okay, now that can be time consuming, but it's doable, and certainly do it, you know. Now, the first place, how did they know near 0? Okay, well, let's take a moment here and look at this. I don't like they just say, here's where your problem is. You need to figure out where the problem is. And what's your problem? Okay, this one has two potential problems.
You have a square root in the denominator.
Okay, yeah, you have a variable in the denominator, which could lead to 0 in the denominator, but you have another problem in that you have the square root there, and square roots can never, what's under the square root sign can never be what?
0.
Yeah, it can't be
Negative.
0. It can't be negative, because you can't take the square root of a negative number. Cube root, you could, no problem there. But any even root, now the index here, if you don't see an index, what do you understand it to be? 2. In most places, if you don't see a coefficient, you understand it to be 1. If you don't see an exponent, you understand it to be 1. But if you don't see an index on a radical, you assume it's 2. That's the only place where your assumption is 2. So we got two things to concern ourselves with. First, the denominator can't be 0, so let's deal with that first. The denominator is the square root of x plus 1 minus 1. You know that cannot equal 0, right? Can't be, ever. Denominator can never be 0. So how do we deal with that? Well, let's add 1 to both sides, okay? And that says the square root of x plus 1 cannot equal 1, because that adds to 0, right? Well, now here's something that's a little dangerous to do. You have to always check yourself. How you solve that for x is square both sides. So that would be x plus 1 cannot equal 1, because 1, the square root squared is just what's under there, and 1 squared is 1, okay? So then you could subtract 1 from both sides, and you have x cannot equal 0. So sure enough, they picked the right value. Okay, x cannot equal 0. But I would still, because we squared both sides, always check the result. So let's see what happens if we did put a 0 in here. If x equals 0, you have the square root of 1. What is the square root of 1? Actually plus or minus 1, but we'll use the plus 1, and 1 minus 1 is 0. Sure enough, that would make your denominator 0. Okay? So, and by the way, that's a principal square root, so it can never be negative anyway. So yeah, so x cannot equal 0. But the whole other thing they're ignoring here is also, since the radical is there, you know what's under the radical, x plus 1 has to be, and what did you say was the condition on that? Anybody? It cannot be negative. How do we express that mathematically? How about this? Is greater than or equal to 0. That would be not negative, right? Greater than or equal to 0. That means it's not negative, right? So let's solve that. Subtract 1 from both sides, and that gives you x is greater than or equal to negative 1. So it could be a negative 1. That would be okay. This would be 0 then. 0 minus 1 is minus 1. But it can't be anything less than that. Negative 2, don't even go there. So you do have some other limits here. Certainly it can't be 0, but it also has to be greater than or equal to negative 1. So in other words, to put these two things together, then I'm going to flip this around. Negative 1 is less than or equal to x, and x is not equal to 0, okay? But x could be, you could go all the way to positive infinity. Now that's a weird way to do it, but I guess the better way is this. I'm sorry, I erased too much. Less than or equal to x is less than 0, and 0 is less than x is less than positive infinity. That would be the best way to do it. Okay? Now that is what I call set notation, kind of. Here's the other way you could express that. X has to be in negative 1 to 0, union that with, I don't need that. Started to put a comma, but I don't need a comma. Union that with 0 to infinity. That's what we call interval notation. Have y'all used that before? Okay. If you have less than or equal to, that means you put a bracket. The equal sign requires a bracket. No equal to that, so you have to have a parenthesis. No equal here, so it has to be a parenthesis. And infinity is not a number at all, so it's always infinity. So there's actually your domain. Okay? All those values. We're worrying right now only about the 0. This one right in here. Not equal to 0. Okay? Now, they want you to evaluate the function closer and closer to 0. Don't go to negative 2. That's too far away. Negative 1 would be okay. Negative 0.5, negative 0.1, negative 0.01, negative 0.001. You can go that route if you want to, figuring out what those are. And then you can go on the right-hand side and do 0.001, 0.0001, anything beyond that. And see if you see where it's heading. You want me to show you the algebraic way to do it? Okay. I really don't like, I would say, wasting or spending all my time doing all those calculations. So here's what I would do. Can I erase what I've got so far? Y'all got that? Okay. Let me show you the technique. Okay? What we're wanting to do is evaluate this thing right here. Okay? Now that's messy, isn't it? Because you got a radical in the denominator, you got a difference in the denominator, and the difference is not all under the radical. It's just messy. Now, do you remember back when you were studying radical expressions, how you didn't like having a radical in the denominator ever? And what we would say then is rationalize the denominator. You remember that? Okay. What were the two techniques? If all you had was a radical in the denominator, then multiply by the radical, and you lose the radical, right? Or multiply by whatever it's going to take to do that. But if you have a radical and a non-radical part separated by a plus or minus sign, you remember what you multiplied them by? The conjugate of that. Who said it? Way to go. The conjugate of that. What is the conjugate of this expression? Anyone remember? The square root of x plus 1 plus 1. Very good. But if you multiply the denominator by that, what have you also got to do to be fair and democratic about it? Multiply the numerator by the same thing. Why? Because what is this over that? 1. When can you multiply by 1? Anytime you want to. Okay? So, multiply numerator and denominator by that. So what does that do to our denominator here? You multiply those two together, right? And, say again? You lose the square root because what you're multiplying is the sum times the difference, or the difference times the sum of the same two numbers, like a minus b times a plus b. And what do you get? A squared minus b squared, right? So your a here is your square root of x plus 1, so that squared is x plus 1. Okay? That's those two squared minus these two squared. 1 times 1 is 1. All right. Now the numerator is quite a bit messier, but just leave it alone. Just write it there. X times the square root of x plus 1 plus 1. Okay? It's messy, but it's okay. Numerators can be messy. But what does that denominator become? Plus 1 minus 1 adds to 0. And what do you have? X. And the x's can divide out. And then what you have is the square root of x plus 1 plus 1. And what's the limit of that as x approaches 0? I can do that. Put a 0 in here, you get 1. Square root of 1, which is 1, plus 1 is 2. The limit is 2. Okay? Now, you can plug in all those values and you'll see it gets closer to 2 from the left, it gets closer to 2 from the right, and here we get it equal to 2. Now, you still can't tell x less than negative 1. That's just out of the picture altogether. But the limit as x approaches 0 is 2. Okay? Now, you could also graph that if you wanted to, and they do it in the book. And it really is the graph of this thing right here, which, do you remember parent functions? Did y'all ever talk about those back in an earlier math? The square root of x is your parent function for all this, and that would be a 0, 0, 1, 1, 2, 4. It's going to be, ooh, that's ugly, half a parabola, half a sleeping parabola, right? Okay. Now, what you're doing with this, you're moving the x, translating the x one place to the left, not right. Plus, you would think it goes right. Always with x, it goes the other way. Translate that one place left and one place up. The y's are the up value. So basically, it's going from here. It's that same shape moved up there. Now, it can have the value x equal negative 1. This is at negative 1 here. But at 0, it has a hole in the graph. Because, and this would be, this is 1 here and 2 there. You're up 1 there. So sure enough, at 1, 2, at 0, 2, you have a hole in the graph. Okay? This to me, so much easier than plugging in all those values and calculating. That's what they want you to do. And sure enough, do it. And you'll see this is approaching 2 from the left. It's approaching 2 to the right. And the limit is 2. Does it equal 2? Yes.
So on the parent function you're showing, you got it at negative 1. Does it shift to the left?
Okay. It shifts to the left 1 because the x, 1 is added to x. And anytime you're doing something to x, go in the opposite direction. If you're adding to it, it'll go to the left. If you're subtracting from it, it'll go to the right. Anything you're doing to the y here being the square root of x, then if it goes up, it goes up. Down, it goes down. If the minus will go down. So the x shifts it in the opposite direction. If you were multiplying this, the x by 2, it's actually a shrink. Okay? If you're dividing by 2, it's a stretch. I mean, it's a stretch this way. But if you're multiplying by 2 out here, outside the radical, that's a stretch, and dividing by 2 would be a shrink. Horizontal, the x always goes backwards on the y. That's how I think of it. It's not a very good mathematical description, but it works. Okay? So does that answer what you said? So this is a vertical, a horizontal shift, left 1, up 1. Left 1 from here, up 1 from there. Okay, the shape stays the same, so this goes up one, this goes left one and up one, this goes left one and up. This is supposed to be at 1 here. My graph is good. Left one and up one. But that's the place where you have the hole in the graph because x cannot equal 0. We did that earlier. I erased it. Okay. I cheated and showed you the analytical way of doing it rather than plugging in numbers. They're going to show you the plugging in numbers, so let's enjoy their show, okay? First thing you do, have to plug in negative 0.01, and you get this value, negative 0.001, you get that value. Now you're doing this to that f of x, the x over square root of x plus 1, minus 1, or plus 1, whatever, minus 1. You get that value, negative 0.0001, you get this one. Obviously, it's starting off pretty close to 2, you're getting closer and closer and closer, so it's approaching 2 from the left. If you go from the right, 0.01 positive on that side of 0, you get this, 0.001, you get that, 0.001, you get that, so you're getting close. Starting off pretty close to 2, but the closer you get to 0, the closer it gets to 2, so it's approaching 2 from the right as well, so your limit here is not defined. You don't have a value for it, but the limit is 2. From the results shown in the table, you can estimate the limit to 2. Now, they show it graphically here, and I was just pointing out, this is exactly the graph that we would get if we did it the analytical way. You would get the square root of x plus 1 in the numerator, nothing in the denominator, and this would be the square root of x. The x plus 1 moves to the left 1, the x plus 1 out there moves it up 1, and then you go like this, but it has no value at x equals 0, undefined there, so put a hole in the graph. But the rest of it looks just like half of a sleeping frog, right? And there is your answer. Now, you can do it either way you want to. You can plug in all those values and calculate and see what it's approaching. Or if you can figure out a way to do it analytically, I like that. Okay. All right. Any questions on that? Okay. Okay. That was example 1. They are skipping example 2 as far as I can tell. Yeah. So let's do example 2. So let me go back. I think I'll do it here. Example 2. Find the limit of f of x as x approaches 2. So what we're looking for is the limit of f of x as x approaches 2. I'm making marks all over the board I don't need. Okay. Where f of x is a piecewise defined function, which is defined to be 1 when x is not equal to 2, and at 0 when x is equal. Perhaps I say it right and write it wrong. Okay? Okay, is equal to 2. Okay? You could plug in values, but it's sort of a kind of a ridiculous thing to do. That's probably easier just to graph this one. Okay? Here's your x. Here's your y is equal to f of x. And by the way, I don't know who you had. I know who some of you had for pre-calculus algebra. But one thing I told all my students, what is y? F of x. So when you're plotting things, if all you have is f of x, that's your y. Okay? The y axis, that's your f of x. So if you plug this in here, f of x is always equal to 1 Excuse me. Y'all awake yet? Okay. Okay, here's the only place where it's not equal to 1. So f of x is going to be a horizontal line equal to 1 everywhere out here except there. Okay? Not there. It's equal to 1 everywhere. But when x is equal to 2, your value is 0. So there is your value down there. All right? Now, piecewise defined functions do strange things like this. And what we're looking for is the limit of this function as x approaches 2. So as x approaches 2 from the left-hand side, what's its limit? 1. As x approaches 2 from the right-hand side, what's its limit? 1. At x equals 0, at x equal to, it's not 1, it's 0. But the limit is 1. The value is not 1. So, this is one of those weird situations that the limit is not equal to the value of the function. Okay? The others we ran into, the function didn't even have a value there because you can't divide by 0. You just have holes in the graph. This one, it does have a value not equal to the limit, but the limit still is 2. Okay? Now, again, these are weird things, odd things. You don't really run into them that frequently, but if you did, the limit does exist. Okay? Now, they say at the bottom there are 3 approaches. A numerical approach, what we did when we did the table and put in all the values. The graphical approach, which I'll show them here, and then the analytical approach is what we use up there. Okay? If you can do it analytically. Now we're moving to where limits that fail to exist. Okay? Here is the thing we're going to investigate. What is the limit of the absolute value of x divided by x as the limit as x approaches 0? Okay? Does anyone remember how we define the absolute value function?
It's always positive.
Second?
Absolute value is always like positive.
Is always a positive number. So how would we express that sort of analytically? The absolute value of x would be x, it's a piecewise defined function, x anytime x is greater than or equal to 0, right? If it's a positive number, it is the positive number. But what is it when x is less than 0? It has to be a positive number. Well, if x is less than 0, then negative x is positive, right? The opposite of x would be positive. If x is positive. But if x is positive, you just use x. So that's how we define that. So therefore, this limit would be this thing here, absolute value of x over x, would be defined as a piecewise defined function as the x over x anytime x is greater than or equal to 0, right? Or minus x over x anytime x is less than 0. You see what I've done? The x in the denominator stays x. The absolute value takes on those values in the numerator. Well, what is x over x? 1. And what's minus x over x? Negative 1. So therefore, this thing is also 1 when x is greater than or equal to 0, and it's negative 1 when x is less than 0. Right? All right. Now, what we're asked to do is the limit of that. The limit as x approaches 0 of absolute value of x over x, what would that be? Well, again, this one just seems like it smacks with do it graphically, okay? If you were going to do this, here's how this would look, okay? As x approaches it's f of x is 1 when anytime x is greater than or equal to 0. And it's minus 1 actually I know there's an open circle here going this way, okay? And I want to say there's an open circle on both of them, but actually they probably put a closed circle on the top. No, they do an open circle. They do it an open circle at both. Because, guess what, team? As x approaches 0, there is no limit. It's negative 1 approaching from the left, positive 1 approaching from the right. That has no limit. So this thing, well, obviously, x can't equal 0, can it? You can't divide by 0. So therefore, it's open circle here, open circle here. We had that before when it got defined in the denominator. But guess what? Every other time they were approaching the same value. This time they're approaching different values. So this limit does not exist. Does not exist. That's not a 1. That's a D and E. Does not exist. Okay? All right. Does that make sense? And those are open circles there. They may not look like it, but that's what they are. Okay. Let's see how they do it. Okay. Consider the graph of the function. Okay. And they just draw the graph as if it was obvious. Okay. Well, no, they do go down here and say absolute value is that. And they don't show you then how they go from this to that, but you do the absolute value over x, okay? And that would be x over x, which is 1, and minus x over x, which is minus 1. That's how they came up with those two values. But both of them have open circles here because in both cases you cannot ever have x equals 0. So this is an open circle here and an open circle there. And they've done something else that's a little bizarre. They threw in a minus delta and a plus delta. I don't know, did y'all recognize these? This is the Greek lowercase delta. Uppercase delta looks like a triangle. Lowercase delta looks like that thing. Okay? And mine look even worse than that. And basically what they're leading to is a formal definition of a limit. We're not there yet, but you can't have delta. As small as you let delta be, they're never, ever going to approach the same value. If this is minus delta here, it gets closer and closer. It still is minus 1. Up here is still plus 1. No matter how close you do, even if they collided, not defined there. And there's no limit because, now, what's the limit of this as x approaches 1? As x approaches 1, alpha of x is 1. As x approaches negative 1, it's negative 1. So any other value, you have limits, but not there. Because there the twain do meet, and they won't. They can't possibly. So that has no limit as x approaches 0. Has limits in other places, but not at x equals 0. Make sense? Okay. Oh, okay, here they did the other part. You said you can see that because of the absolute value is defined that way, then your absolute value divided by x is minus 1 for x greater than 0. And see, that's where I made an error. Where did I write this? Oh, I erased it all. So I said, because this is greater than equals 0 here, I put a greater than equals 0 here. No, it's not. Can never be equal to 0. So that's just a greater than 0. I did do an error there. Sorry about that. Okay. So no matter how close to x gets to 0, there will always be that huge discontinuity there. The positive and negative x values will still yield f of x equal 1 or negative 1. Specifically, and this is where the delta comes in, if delta, the lowercase Greek letter delta, is a positive number, then for x value satisfying the inequality, 0 is less than absolute value of x is less than delta. Now, the absolute value here allows us to be over here or over here. You can classify the values of x over absolute value of x over x as -1 or 1 in those intervals. No matter if delta is a positive number, minus delta is a negative number. So in there it's always equal to -1, and in this interval it's always equal to +1 of delta is positive. No matter how small you get on delta, it's still going to be that way as long as delta is greater than 0. Okay? 0 is less than delta. Not less than or equal to, less than delta. So no matter how small you get, 0.000000000001, okay? Still going to be a +1. Or negative 0.0000000. It's always going to be a -1. So narrative, you can't ever break that. They jump as called a discontinuity, jump discontinuity. We'll get to that later. Okay, it looks like we're going to have to start with example 3 next time. Okay? No. Oh, no, I'm sorry. Because of that? Okay, yeah, we've already said that. So, we're going to start with example 4 next time. And then we'll hit this slide here. Okay. Any questions? Sorry, we should have gone a little further. Let's see if there's any homework exercises for you. I think you can do any of the odds 5 through 9. Okay? I think you can do any of the odds 11 through 17. Oh, maybe not. Let's do 11 through 15. By the way, all the odds have answers in the back and are at calcchat.com. Number 5 is also at calcview.com, and you can do it on your Q2 code. Is that what you called it? Huh? The square code Q2?
QR code.
Huh? QR code. QR code. Okay. You can do it.
Numbers again one time, please.
Any of the odds 5 through 9 and 11 through 15. All the odds have answers in the back and are at calcchat.com. Number 5 is at calcview, and you can hit the code and get that. Good deal. We'll see you next week, once a week, every week, whether we need it or not, right? Okay. But we'll hopefully get caught up.